let me check. Yeah, so it's working, so you can start whenever you want.
Okay, thanks, Diego. So, well, I'm going to be brief. So, first of all, I would like to say good morning or good afternoon, depending on the time zone, to the people that have just connected and that just arrived. So, welcome here to another of the seminars in this series associated with the IDEAIS project. For today, we are going to be having two short presentations by students from the University of Lisbon, from Instituto Superior Técnico. Okay, so both these presentations today, they are related to the theme of the project, and specifically they relate to using natural language to try to support the access to geospatial information. Okay, and both presentations that you are going to see here today, they correspond to work that was recently accepted for presentation at a conference in the area called ACM6 Spatial. Okay, so these things that you're going to be seeing here, they are later going to be presented also in the context of that conference. So specifically, first, we'll have a presentation from a student called Rita Ramos, a PhD student here in Lisbon. She'll be presenting a short work on image captioning, on remote sensing image captioning. Okay, and after that, another student, a master's student named João Coelho, is going to make a presentation that's going to be a bit longer and specifically focusing on geospatial question answer. Okay, so this task that has to do with providing natural language answers, or specifically retrieving paragraphs of text that contain the answer to a natural language question that concerns geospatial information. Okay? Mostly factoids, but yes, João is going to be talking about that, and you'll see in a bit more detail later on what the problem is. So yeah, I guess this is it, and I can pass the word to Rita, that can make the first presentation and present this work that she's been that she developed a few months ago on remote sensing image captioning. Okay, so Rita, when you want.
Hi everyone, I'm here to present, as Bruno said, the paper Remote Sensing Image Captioning with Continuous Output Neural Models by me and my supervisor. In this work, we explore deep learning methods for the task of remote sensing image captioning, a challenging task that involves generating a description for an input aerial image. There has been a lot of research for the general image captioning task that involves generating captions for natural images, whereas research on remote sensing image captioning only recently started. And note that the images are very different from the natural images, which imposes different challenge, right? For instance, you can see that for natural images, the model has to pay attention to a small number of objects, whereas in remote sensing image, there are many regions of interest to pay attention to, and the scales of the same type of objects may vary significantly, like these planes. The typical approach for these tasks involves the standard encoder-decoder approach for general image captioning. Most studies have been focusing on the attention mechanism, so proposing attentions that are specifically designed for remote sensing images. In fact, the current state of the art was achieved with a novel multi-level attention mechanism. So typically in most studies, a CNN is used as encoder to represent the image, and then this representation is given to a LSTM decoder to generate the caption word by word. This is also combined with an attention mechanism to weight the image parts that are more relevant for the current prediction. Note that the decoder generates each word using a softmax layer, which produces a probability distribution over the entire vocabulary, and then samples from it. But recently, an alternative approach for language generation was suggested by Kommer and Svetskov in the context of machine translation, replacing the conventional softmax layer with an embedding layer. Well, it's common to use pre-trained word embeddings in the input layer, but here their idea is to use embeddings as outputs for language generation. So they propose an embedding layer as the final output layer instead of a softmax layer. In this way, the model can generate word embeddings, so a word vector, rather than probability distributions over the entire vocabulary. Therefore, overall, this method replaces the generation of discrete outputs with continuous output representations. Their main motivation was training efficiency. The authors wanted to alleviate the burden of using a softmax layer, which becomes very expensive as the vocabulary size increases. But we further note that the typical approach, relying on discrete outputs, optimizes at token level. Their idea is just matching the generated sentences versus the reference sentence word by word, whereas the generation with continuous outputs can be optimized in respect to semantic similarity by minimizing the distance of the predicted embedding and the target word embedding, as opposed to exact word-by-word matches. So in this work, we argue that language generation with continuous outputs can also potentiate the use of novel loss functions to optimize semantic similarity at different granularities, at token level, at sentence level, and at image level. Therefore, continuous output models have potential to capture the global semantic similarity between captions and images by using loss functions that compare different views of the data, not just at token level. So in this work, we propose a continuous output model, encoder-decoder for remote sensing image captioning, and we design a new loss function for continuous outputs that goes beyond token level optimization. I will now explain in detail the aspects of the proposed approach. I will start by the encoder. As I said, the main innovation of our paper relates to exploring continuous outputs in the decoder side, but we also explore a novel encoder for remote sensing images. As in the task of image captioning, most remote sensing image captioning studies use a CNN encoder pre-trained on the ImageNet datasets. However, the ImageNet dataset only contains natural images, which have very different characteristics for remote sensing images, which, as we mentioned before in the beginning. So in this work, we propose to fine-tune the encoder on the original remote sensing image captioning datasets, so using in-domain data, to get better image feature representations. Specifically, we use the EfficiencyNet model, and we propose the fine-tuning task related to prediction the caption embeddings obtained by averaging its word embeddings. So use natural language supervision to train our encoder within domain data. Regarding the decoder, the language generation is a LSTM model that contains an embedding output layer in replacement of the softmax layer. So the model generates sequence of embedding vectors instead of directly predicting word tokens. And this decoder is also combined with a neural attention mechanism, in this case, a simple scale dot product attention. Okay, regarding training, the caption model is then trained with a novel loss function, specifically designed to explore generation with continuous outputs. These loss combine three separate terms, optimizing similarity at token level, at sentence level, and also at image level. At token level, the smooth L-in loss is computed between the predicted embeddings and the target token embeddings. At sentence level, the smooth L-in loss is computed between the mean of the predicted word embeddings and the mean of the target word embeddings. So this compares the generated caption and the reference caption. At image level, the smooth L-in loss compares the generated caption against the image. Okay, this was at training time. At S time, each word is generated from a predicted embedding by selecting the word of the vocabulary that has the nearest embedding. So in this case, the one that would be predicted, chosen, would be the word plane. Specifically, we proposed a tailored beam search that explores continuous outputs, going beyond the standard beam search by also evaluating the generated sentence according to similarity towards the input image. Okay, let's now talk about the evaluation of the proposed method. Our experience relies on two different datasets commonly used in the area, the UCM and the RSICD datasets. In this presentation, I'll just show the results for the RICD dataset, which is the largest dataset of the area. To evaluate caption quality, use established metrics, such as Blue, Meteor, and so on. Basically, some of these metrics just consider token matches, but others match words at various levels, including cinemas. In the experiments conducted on the RICD datasets, we first verified the effectiveness of the proposed encoder. So both these models use the same decoder based on discrete outputs. Here is the model just differ in terms of the encoder. So either using the EfficientNet model pre-trained as default on the ImageNet datasets, or using our approach of fine-tuning on in-domain data. As you can see, the proposed encoder outperforms by far the standard encoder. This shows that fine-tuning the encoder on remote sensing images leads to better image features representations than just using a CNN pre-trained on the ImageNet. We then assessed the use of continuous outputs for the language generation of the decoder. So this part of the table showed the results of our captioning model using the fine-tuning encoder together with the continuous output decoder trained with the different loss terms. So the first is our model with just the token level loss, then the model with the token level and the sentence level term, then also with the image level term. And finally, our model with all the three terms, but with learnable weights to balance the contribution of each term. And the last line shows the performance of our model using the proposed beam search at test time. As you can see, the proposed continuous output model is by far better than the standard approach of discrete outputs. So the result shows the effectiveness of optimizing semantic similarity as opposed to exact word-by-word matches. The results of our model are also comparable with the current state of the art. And in fact, if you can see that our model achieves the best score in terms of Blue 2, Blue 3, Blue 4, also cider and spicy. Okay, let me just show you some examples. In the first image, discrete approach mentions several green trees incorrectly. In fact, previous studies of the area have reported that there is a tendency to generate information that is not in the image due to the presence of highly frequent words during training, like several green trees, whereas our captioning model was able to avoid this error, correctly generating many cars are parked in a parking lot. So without mentioning the several green trees, thus describing information that is actually present in the image. This shows that, as also suggested by the quantitative results, the qualitative examples further confirm that our continuous model is better at capturing the semantic context of the input images. Okay, let's now conclude. This paper presented a novel encoder-decoder model based on continuous outputs for remote sensing image captioning, replacing the generation of discrete outputs in favor of word embeddings. We specifically designed a new loss that optimizes semantic similarity at sequence level or post-word level. We also presented a novel encoder that is fine-tuned with in-domain data. And the results show the effectiveness of both the proposed encoder and decoder. Despite the interesting results, there are also many possible ideas for future work. For instance, our model uses just a simple attention mechanism, whereas previous studies on the area have proposed attentions that are specifically designed for remote sensing images. So a better attention mechanism should be considered. Furthermore, the proposed model simply uses average word vectors for the sequence level term. So future work can perhaps consider alternative formulations for these sentence level components. And also the CNN encoder and the LSTM decoder can in the future be replaced by the transformer architecture, given that these models are currently achieving state-of-the-art results on several tasks, including on language and vision tasks. This is all. Thank you for your attention. I don't know if you have any questions.
Thank you, Rita. So, well, we can take questions in the end. I guess we can take a few questions here now as well. I mean, if you guys have questions, you can leave them on the chat. You can also raise your hand and we'll try to, well, promote you to panelist or something in order to make sure that you could ask your question here live. In the meantime, to give you some time, I will just make a brief well, comment and question to Rita. So you, Rita, didn't actually address this aspect in your presentation, but we kind of noticed during this work that there are some issues and problems with the data set that is, well, the major data set that people are using in the area, right? And I guess as part of this work, one of the issues that we point to is the need for more data and better data sets in this area in order for the, I mean, if this task is really to achieve progress on top of this, we would need better data as well, right? And Rita, I don't know if you have any additional comments regarding this, if there are additional aspects regarding data quality that you want to mention.
Yeah, for sure. In this paper that you are going to submit to SM6 Special, we didn't inform about that problem that we found out because we made an analysis to the data sets and we found those problems that the data distribution between the validation and the tests are very different. But we'll plan to make a new paper in which we address out those points, which is something that people should invest, people that are working on this area of remote sensing image captioning. Yeah,
there's that, and there's also the issue that so the vocabulary is kind of small, right? And there are a lot of captions that are very similar to each other. Different images end up having very similar captions in the end.
Yeah.
Okay. So there's just another question here in the chat.
Also, there is not a server, a test on a server, so researchers can also easily fit to the test sets. Unlike, for instance, in image captioning, where COCO data sets usually have and held out tests that people cannot fine tune specifically to, so it's people don't have access. And I think it would be great if you had that also in remote sensing image captioning. Yeah.
Oh, I see. So because people see the testing data sets, in some cases they may attempt to use it and to fit that. Okay. Whereas in COCO, the data set, or one of the data sets that people use from it, the test split is actually hidden, right? And there's this form in which people submit, you know. Okay, so Daniela was here in the chat window also asking if there are, let's say, important differences in terms of the method and the network architecture for specifically dealing with remote sensing images versus natural images.
Usually they are very similar. The main difference is just the attention mechanism, because so usually people still use an encoder and decoder, but since there are more regions of interest to pay attention to, that should be paid attention to in remote sensing images, people tend to design specifically attentions that try to address some of these characteristics of remote sensing images. For instance, one of the state-of-the-art combines their attention is basically 3 attentions model. So they give more focus to the attention mechanisms that are usually in general image captioning models. But there are still things that, so in image captioning, people are starting to use a lot of transformers. And I think there isn't that shift yet to remote sensing image captioning, but there will probably be soon. Let's see. But for now, it's just attention mechanisms. I hope I answered your question.
So, Diego, you wanted to say something as well?
Yes, I also have a question. I do not work in machine learning, so my question may be a bit general, but you present this as an encoder-decoder method. Is this an autoencoder, or I got confused and it is something completely different, or is just the same name for the same thing?
Can you repeat if this decoder is what?
If this model is what is called an autoencoder, or is something?
No, so usually these are different things. Okay, so when people use this term autoencoder, they're basically referring to models that attempt to build representations for data, usually for doing, I don't know, unsupervised learning. Okay, and the trick is that you use a neural network to encode the input data that you have in a lower dimensional representation that is good for reconstructing your original inputs. That is why the name autoencoder, right? So you design a network in such a way that it is able to reconstruct the original inputs from the representations that it generates. Here in this case, it's a bit different, right? So this is, I guess, supervised learning in a way. So you're mapping inputs to outputs. And the way that you do this is that your inputs are images. So you have a part of the network that builds a representation for these inputs, the images. And then you have another part, which is the decoder, that from these representations attempts to generate the output, generate the sentences. Okay. So I mean, that's the difference between these terms and what people usually mean when using these terms.
I see. Thank you.
Okay, so I would...
which consists in identifying the top ranked passages in a background collection for some given question. But in this case, we consider the specific case of geographical queries. This is questions that contain entities such as place names. For example, here in the image, we have a query that reads average winter temperature in Kent County, Delaware. And we have a collection of passages, potentially very large, with millions of examples. And the goal is to retrieve the relevant ones, which in this case would be the first one. So the main objective was to build better ranking models for passage retrieval by exploiting the geographic properties of queries and passages, following an intuition that passages that contain entities that are geographically closer to the ones in the question should be more relevant. But before diving into those methods, I'll present some background and related work. So the base neural architecture that was used in this work was the transformer. It is an encoder-decoder architecture, but here I'll focus only on the encoder part, which is depicted in the left picture. And the main objective is, given an input sentence text, we want to generate a contextual vector that represents said text. And for this, it starts by getting static word-level embeddings, for example, word2vec for the input sentence. And then, since the transformer processes the input token simultaneously, there is this positional encoding step based off sinusoidal functions, which is used to approximate the position of each word in the sentence. After this, there is the attention layer, which names the paper that it was proposed on, and it aims to help understanding the relevance of the input tokens for one another. In the right picture, there's the architecture for this operation. Basically, during model training, 3 linear layers will be used to learn 3 weight matrices, V, K, and Q. And the original encoders have 8 attention heads. This means that there are 8 independent sets of matrices. And the formula on the bottom right is used to compute the scaled dot product attention for each one of the sets. Those results are concatenated and then fed to a linear layer. The output of this linear layer is fed to a feed-forward network, whose output is fed to the next encoder if there is one. And the output of the last encoder is the representation that we are looking for that vector for the words. Now, here's BERT, which is a language model that is built on top of the architecture that I just showed. These yellow boxes here are just stacks of transformer encoders. BERT large has 24 encoders, while BERT base has 12. I'll go briefly through the training process, which consisted in 2 tasks. In the first one, the input words were masked, some of them, and the objective was to guess which is the original masked word. This is referred to as masked language modeling. The second one is called next sentence prediction, and basically given 2 sentences, we concatenate them with a special token, the SEP token in red in the picture, the right picture. And the objective is to guess whether or not the second sentence does follow the first one. These are fully self-supervised methods, which means that the only thing we need to train is raw text. And as such, BERT was originally trained on lots of Wikipedia articles and books. Okay. So far I showed an overview of how the language models work. This is how they generate the representations and their training. And now I'll address what we do with those representations. So we are dealing with passage retrieval. So we want to score passages with respect to queries. This is, we want something that, given a query and a passage, returns a value of relevancy. Here we do that following 2 different architectures. On the left, we have the bioencoders, which, for example, take BERT as a language model, and it is used to encode queries and passages independently. So after encoding, we have a vector for the query and another for the passage. And then to get the relevance, we use the cosine similarity between the vectors. They are very efficient, and due to this, they are used for full retrieval, which is the task of getting the top k ranked passages over the whole very large collection. On the right, we have the cross encoders. The main difference is that they generate the representation for the concatenation of a query and a passage. This is, we concatenate them, and once they go through, we have a vector for the concatenation, not 2 vectors, just 1. And then this representation is fed to a linear layer to generate the similarity score. While they capture the interactions between the 2 sentences a little bit better than the bioencoder, they aren't as efficient because we have to pass all possible pairs through this network, and hence they are used for top k re-ranking. This is, we first obtain the top k from an efficient method, and then we re-rank the top k using this cross encoding. Okay, so as for related work itself on passage retrieval, here I'll briefly discuss Rocket QA, which is a system that leverages both cross encoders and bioencoders. They start by training a bioencoder with a technique called cross-patch sampling. This means that they are training in multiple GPUs and share the training examples across the GPUs. And then they use this dual encoder to sample negative training examples when training a cross encoder. They use the first bioencoder then again during the training of another bioencoder, but the previous cross encoder is used to denoise those negatives. This is, negative passages that the cross encoder scores very highly against the query are considered false negatives, and then they are not used during the training. And finally, they also augmented data, and for this they retrieve passages for unlabeled queries using the previous dual encoder, and then they use the cross encoder to label those queries. And this is a very heavy architecture in terms of training, since it requires multiple models just for sampling and augmenting data. But the final result is a very efficient dense retrieval method, which achieves state-of-the-art results when it was published. As for related work in geographic information retrieval, there are some studies on the semantic and syntactic structure of geographic questions. For example, there was this work that tried to generate generic forms for questions and question-answer pairs, considering the relationship between the geospatial entities in both. And for geographic question answering, there is, for example, a system that enriches those numerical vectorial representation of sentences with their geographic properties. And there is also a retrieval method that uses listwise learning to rank, where some of the training features are geographic. So I'll go now into the data that we use in this work. MS-MARC is a large benchmark data set for passage retrieval. It has over 1 million queries and 8 million passages. And other authors have studied the geographic contents of this data set, and under their own definition, they found 12,548 question passage pairs. But to follow that intuition regarding the proximity between entities, we needed to resolve those textual entities to geographic coordinates. And there is this open source tool called Mordecai that does exactly this. And we used it to pass MS Marco. We considered a query to be geographic if it contained an entity that Mordecai could resolve into coordinates. Here is an example of how we did that. So for a query, we start by concatenating a query to its relevant passage. This was done to avoid some errors because since queries are small, they are uncontextualized, and Mordecai may misrecognize some entities. In this specific example, if we processed the query alone, it would recognize Myrtle instead of Myrtle Beach, which would cause some problems because when parsing the passage, it would identify Myrtle Beach, and then the coordinates would be different, which is not what we are looking for. So this concatenation is fed to Mordecai, and Mordecai's output is shown here on the right. It contains some information, including the, I have something in front of my screen, sorry. Okay, including the entity and the coordinates, but it also shows the span. And the span, we used it because since we have the passage there, we want to exclude entities that were recognized only in the passage. So after this, we were able to extract the geographical subset of MS Mark. The original data set has publicly available train and development sets with their respective labels. And from the development set, we extracted 292 geographical queries, which we used as our test set. And from the training set, we extracted 16,833 geographical queries. And from those, 292 were sampled to be used as a validation set, and the remaining 16,541 were used for training. All these queries have associated with them their top 1,000 passages as retrieved by BM25. So as for our approach for geographic passage re-ranking, I will start by showing our definition of distance between queries and passages. So given a query and a passage, we can extract the set of entities in the query, which is here represented by TQ, and the set of entities in the passage, which is represented by TP. And basically our distance is the minimum Aversign distance, the bottommost equation, between every pair of query entity and passage entities. So what we did was we fine-tuned both bi-encoder and cross-encoder models. And for that, we used the previous definition of distance when sampling hard negative examples for training. And then we also used the knowledge distillation process from the cross-encoder to the more efficient bi-encoder. I will start with the negative sampling method. So for a given train query, we have its relevant passage, and we can build a pair query positive passage. But what about the negative examples? Remember that there is a collection of 8 million passages, and in average, only one is positive, so we have a lot to choose from. But if we choose examples that are very different from the relevant passage, this will be too easy and the model won't learn much. So what we did was we chose passages that were lexically similar to the relevant one, but geographically distant. More specifically, for a given query, we picked its top 25 BM25 passages, and from those, we extracted the 10 ones with higher distance to the query. Now that we have the training examples, we need to build training batches. And as I said, each query has on average one relevant passage, and I sampled 10 negative ones. So by repeating the positive passage, we can build 10 triples of query, positive and negative. Each batch will have a fixed number of triples, and batch-wise negative pairing was applied. This consists in using the positive and negative passages of a given query as negatives for the others, which increases the effective training data. And since this was used, we also used similar query batching. Here, the intuition is that if a passage is hard for some query, it will probably also be challenging for similar ones. So we batched similar queries together. Okay, as for the training setup, we start with pre-trained cross-encoder and bi-encoders built on top of Electra and Roberta, respectively. We used a batch size of 4 and the cumulated gradients for 10 steps, and the loss function was the standard binary cross entropy. This was kept the same when training both bi-encoder and cross-encoders. The only difference is on computing the relevance score. Previously, I showed the architectures, and for cross-encoders, the score came from the linear layer, which is obtained by applying the sigmoid function to the log x vector. But for the bi-encoders, we have to perform other normalizing operations because the cosine similarity doesn't portray a good separation between positive and negative examples. And as such, we built a matrix one matrix per batch with the cosine similarity between the queries and the passages, and it was soft-maxed row-wise and column-wise. And finally, we have the knowledge distillation method. Here, the objective was to try to further improve a dual encoder, which is more efficient, using a cross encoder as the teacher model because it produces better relevance estimates. One approach for this cross architecture distillation is to fit the teacher values directly. But as I just said, here that can't be really applied because the range and magnitude of cross encoder similarities differ from the bi-encoders. This is why we use the method which considers the ranked list of scores instead of the scores themselves, which is possible because of previous work on fully differentiable soft ranking. I have here an example. So imagine for a given query, we have a batch of 4, so we have 8 passages associated with it. The cross-encoder pre-computed its scores for these passages, and we can have a ranked list, this one on the right, 1, 8, 2. And then during training, the dual encoder will also produce the scores, and we can use the differentiable soft ranking operation to produce the ranked list. Here we have that P1 ranked 8 with a score of 0.1, P2 ranked first with a score of 0.9, and P8 ranked second with 0.8. So we have these two lists of ranks, and we can compare them, for instance, using the Spearman's rank coefficient. Okay, I'll get into the results now. First, we evaluated on the geographic subset of MS Marco. The first group is about BM25 and re-ranking it with the geographic distance. And we can see that this actually improves the results, which is why we pursued the idea of using the geographic distance to sample the negative. And we can also see in the following groups that following our fine-tuning strategy does improve the base models. The bi-encoder went from a mean reciprocal rank of 0.40 to 0.42, and the cross-encoder went from 0.49 to 0.51. However, we can see that the naive usage of the distance re-ranking on top of the neural models is not good. The final line presents the result of the distillation process from the fine-tuned cross-encoder to a bi-encoder, which achieved the 0.429, which is slightly better than the previous bi-encoder. We also evaluated on the full MS Marco. This is the full set where some of the questions are not geographic. And this was done to assess the impact of our fine-tuning strategy on other types of questions. The fine-tuned cross-encoder does achieve better results than the base one, but the bi-encoder model, both the simple fine-tuned and distilled one, seem to overfit the geographic domain since the results are worse than the base model. We also present an hybrid model. Here, since we know a priori which questions are geographic and which are not, we use our model to rank the geographical ones and the base model to rank the others. The fact that the fine-tuned cross-encoder achieves better results than the hybrid version is interesting, and it may be due to the fact that some of geographical queries don't necessarily need to contain entities explicitly, and our model may be better at ranking those queries than the base ones. Here we have a follow-up table from the previous one. MS Marco has some associated types with each query. For instance, a location query is a query whose answer is a location. Both fine-tuned and cross-encoder and bi-encoders are better than the base models for these location queries, which is ultimately what we expected. But while the fine-tuned cross-encoder only gets slightly worse when answering to person queries, the fine-tuned bi-encoder shows that overfitting to geographical domain behavior here because it only answers better locations that are location or entity. So that we could understand these results a little bit better, we used SHAP to identify which tokens the models are paying attention to when ranking. Here we have the base and the fine-tuned cross-encoder for a question passage pair. And we see that some of the attention is being given to the relevance token in both of them, but the fine-tuned version concentrates the attention much more, which is probably why the fine-tuned version achieves better results. And the same behavior happened here when dealing with bioencoders. I'll wrap up with some conclusions and future work. So we inspected MS-MARC, and it contains a considerable amount of geographical content. We proposed a fine-tuning strategy from which passage re-ranking models seem to benefit. And we were also able to further improve the bioencoder models with the distillation process. And as for future work, we can explore the fine-tuning technique in other domains. For instance, temporal entities also have an inherent distance. And the fine-tuning method itself can also change. For instance, we can use a cross-encoder to sample the initial list of negatives instead of BEM1025. Here, we would be following a semantic similarity instead of lexical similarity. And it would also be interesting to use other efficient retrieval strategies that differ from the standard bioencoders, such as Colbert or Sparta. Okay, this was it. Hope it was clear and that you enjoyed it, and I'll be glad to answer any questions you may have.
Okay, thanks, João. So again, I guess we can take questions in the chat window, or if people want to ask the questions live, they can also raise their virtual hands here. Well, to give some time, I'll just start with a brief comment in the sense, well, I guess this was also clear from your presentation, but this work here kind of focuses on one type of geographical question, which is mostly about factoids, right? What is the city that has a given property? What is the capital city of somewhere else? Things, mostly things that one can answer from the web or from Wikipedia, right? But there are, of course, other types of geographical questions as well. Things that are, I guess, best answered with basis on a map, or things that involve, let's say, geoanalytics, involve a process to compute the answer, right? Which was not the focus here. So, I mean, this area of geographical question answering is very broad. There are lots of very interesting challenges. João only addressed a minor thing here, a small topic. Well, independently of this work from João, for instance, I think it would be also very interesting to work on classifying the types of geographical questions. So depending on the question, figure out what is the right system to provide the answer. And I think that's probably can be something, some way of achieving progress, right? In the sense that there are going to be some questions that require something like what João just presented. And there are going to be questions that require a program, right? Similar to the, well, a program that combines tools from the GIS tool set in order to compute the answer. So, Diego, if you kind of have a question, I guess, go ahead.
Yeah, I actually have two. One of them is somehow related with your comment, and is an open question, because you work a lot on this intersection of machine learning with geographic data. So my question was, what, in your opinion, what are like the hot topics right now in this intersection?
There's a lot of work going on, a lot of things that are still open. I think overall, there's a lot of interesting work to do in bringing in what people know in GI science as regularization strategies for machine learning models, right? So make sure that you design your machine learning models with the inductive biases that people know to be true of geographical phenomena. And this includes things like, I mean, even simple things like Tobler's law, you see? So make sure that when you design your models, well, you kind of expect that the predictions for things that are located close by should be similar, right? So design your models in a way that encodes this. And similar to this very simple rule, there are others that are, well, familiar for people from GI science, right? And that can influence how you design these models, okay? So make sure that your predictions present a degree of spatial autocorrelation that is compatible with what you know about the phenomena, things like this. So for me, one hot topic in this geospatial AI is this, okay? So bringing knowledge from what people know in the GI sciences into how machine learning models are designed. Okay. And then there are many other topics. I mean, of course, this is also an area of interest to me, but the specific area that the IDEAIS project focuses on, which I guess is this interaction, right? So use language and use different ways for people to interact with GIS and with geographical information. It's also quite interesting, and this, I guess, requires and goes through machine learning. So all these problems that have to do with translating natural language into ways of interacting with GIS software, I guess it's still an open issue, right? So there's been work on that for years and years, but it's still a problem, right? It's still something that people don't know how to do.
Okay, thank you. And my second question is, okay, this works for English language, but how hard is it to adapt, for example, for Portuguese or to Spanish? For example, there is a Spanish version of BERT, which is called Beto. Everything will work if we just replace BERT with Beto, or it needs a lot of fine-tuning and these things? For example, are you thinking about adapting this to Portuguese?
Okay. I can answer that because probably I am aware of of some recent things. So it is challenging in the sense that, okay, you have these large language models for other languages as well. But for these retrieval problems, like the one that João just presented, you kind of need to then further specialize these models to the task. Okay? And this requires data. So João didn't just take on BERT and that's it, right? So he specialized BERT with the data set called MS Marco for these retrieval tasks. And that's why he obtained these models that perform well. And so you kind of need data, right, in order to make these things work. And this is a problem in the sense that this collection, MS Marco, for instance, it's very large. It costs a gazillion of money to build. And I don't think anyone is going to do a similar effort again anytime soon in the future, right? So MS Marco was built by Microsoft. And I think I saw an estimate once for how much it cost to build the collection, because they had humans annotating the passages that were relevant for the queries. And it was a huge amount of money. Okay, so there's no way that a small group in a university would get the funding for doing something like this. So we won't get a Spanish Marco anytime soon. But some people have tried to go around that by using machine translation. Okay, so what you do have is versions of MS Marco that have been automatically translated to other languages, Spanish, Portuguese. There's actually some strong groups working with the Portuguese versions of this. So yeah, to some degree, you can work on these problems for other languages. You can use through these tricks the existing data sets to try to adapt these models to other languages. But I mean, as in other language technology areas, yeah, there's much more work done for English than for other languages, and that's still true.
Thank you, Bruno.
Okay, so I'm not sure if we have additional questions here in the chat window. Yeah, so I guess, Diego, what do you think? I guess we can probably close and end this session here, right?
Yes, yeah. Thank you.
I don't know if you want to say anything about the cost action, the IDEAIS CITED action, and about the next meetings like this.
No, just to thank you all for your time. I wish you luck with your presentations at the conference. Very interesting works. So good job, guys.
Okay, thanks.
Thank you.
And
Thank you.
yeah, so and I guess so these these monthly seminars, right, will head back and will receive news regarding the next one, right?
Yes.
Okay.
Thank you.
Thank you.
Bye.
Bye-bye then.
Bye-bye.
Bye.